Okay, let's go on to some examples. So here's example one. Pretend this is data from 3 different kinds of pizzas. Let's say it's, I don't know, for medium, large pizza. I think this is actually sort of a conservative estimate of grams of fat. So let's say this is Papa John's pizza. It has 100 grams of fat per pizza, but the cost is $17.50. But Domino's, let's say, is 110 grams of fat per pizza, but the cost is $18. And Pizza Hut's has 120 grams of fat, but the cost is $20. So maybe we might have a feeling that maybe more fat makes it taste better, so it costs more. I don't know. Who knows? But the question is, which of these following equations fit this data the best? Okay. So in order to solve this problem, we'll have to find the sum of squared errors for each of these equations. And right now, we're not sure if any of these equations is really the regression line. Maybe we're just trying to find the best equation out of the 3 that we have so far, right? So which of these fit the above data the best? This means which equation has lowest error, right? Or sum of squared error, right? So if you pull up your the examples provided for you in the Excel file and click on example 1, I've already entered in for you the data right here. So here's our 3 pizzas, the fat, as well as the cost. And it seems, just from eyeballing it, that there is a positive trend, right? So as fat goes up, cost goes up. We don't know why, but it seems to do so. So let's go ahead and put in our, you guys aren't supposed to see this. Let me just delete this. Let's go ahead and try with the first equation that we were given. The equation said y equals 4.75, that's the intercept, plus 0.1x. And so I've separated it out into the intercept as well as the slope because we're going to need those numbers. And so here's the fat, here's the cost. Let's find the predicted cost, or y hat. And in order to find y hat, all we have to do is plug in our x into our line equation, right? So that would be this value, 4.75, and that's not going to change, so I'm just going to put, so I'm going to lock it in place and add that to B1 times x, right? And B1 is not going to change either, so I'm going to lock that in place. All right. But we do want B12 to keep changing, right? And so I'm going to take that predicted cost. So that predicted cost is a little bit less. And then I'm just copying it and pasting. And so these predicted costs are always a little bit less than the actual costs, right? And so here, all of our residuals are going to be, so the residual, if you remember, is the actual cost minus the predicted cost, right? So all of our residuals are going to be positive, right? And that's that case where all of our actual data actually are above our line, our prediction line. And so because of that, we know that this isn't quite a good, it's not a great regression line. Who knows? Maybe it has the smallest SSE though. So now we have our residuals, and all I'm going to do is take this residual and square it. So I could find all my squared residuals, and then in order to get the sum of squared residuals, I just add them all up. Okay, so I get 23.1875 as my sum of squared errors. And so who knows, maybe that's the lowest one. We'll see. So here, I've put in the data for the next equation. So it's y equals 8 plus 0.025x. So I've separated it out into the intercept versus the slope. And let's find the sum of squared error. So to find the predicted cost, I need to add this, take my intercept, lock it in place. Oops. Oops. Lock that in place. And add that to my slope times x. And I'm going to lock my slope in place as well. Oops. Keep. All right. So right now we're a little bit low. Still low. Still really low. So already I could see that because our predicted costs are more off than these predicted costs, I'm going to guess this sum of squared errors is going to be considerably larger. And so let's find the residual. Remember, the residual is the data minus the predicted. So data minus the predicted. And then all I do is square that residual. And then sum them all up. And as I predicted, because all of our predicted costs were more off than these predicted costs, this equation is much better than this equation. Now let's test out the third one. Oh. Okay. So hopefully you didn't see those answers. Let's see what the predicted costs look like. Well, we want to add our intercept with our slope, lock that in place, times the x, or the fat. Now, Excel will automatically do order of operations, so I don't have to put parentheses around the multiplication. It'll do the multiplication first. And we see that this is actually quite close to the cost. It's off by a little. It's sort of it's off by 25 cents, but just below. Let's see about the next one. Now this one is off by a little, but in the opposite direction. It's off in the positive direction. And this one is off a little bit in the negative direction. So this seems like pretty good prediction. We're getting pretty close to the costs. Let's find out what the residual is. And here we should have a mix of residuals, some positive, some negative. So cost minus the predicted. So we have two positive ones and one negative one. And in order to sort of, and they balance each other out quite nicely because the positive ones are smaller, but the negative one is a little bit bigger. And let's square those. And so here, if we sum that up, we get 0.375, and that is considerably smaller error than 23 and 182, right? And so I'm going to say the third equation is the best fitting one. So this one is the best one. So here's example 2. Now it gives us the same data and asks, find the regression line for these data points and then interpret it. Okay. So if you go back to our Excel file and click on, example 2, then you'll see the data here for you. Now, first thing we probably want to do is figure out all the different things we'd like to get. And I'm just going to use a little bit of a shorthand. instead of writing x minus x bar, I'm going to write deviations of x. So deviations of x. And I'm also going to need deviations of y. And then I'm going to need to multiply the deviations of x times the deviations of y. And I'm also going to need to find deviations of x squared. Right? So these are the 4 things I need. But in order to get these, I'm going to need x bar So here I'm going to put averages, right? I'm going to need to find x bar and y bar, and that's right here. So here I'm going to put an average and find my x bar, which is fat, and also just copy and paste that over to find y bar, the cost, the average cost. So my point of averages is 110 and 18.5. So now let's find all the deviations of x and do all this stuff in order to find slope. So the deviations of x is x minus my x bar. And so here I'm going to lock my x bar in place. There we go. And then I can just copy and paste all the way down. Let's also find the deviations of y, which is cost minus the average cost. And then I could just copy and paste that all the way down as well. Notice that my deviations of x and deviations of y, they're sort of like helping us towards that lowering of the residual idea. Because the deviations of x, if you look at all of them, they're very balanced, right? So half of them are on one side of the average and half of them are the other. By definition, that's what average means, right? And so are my deviations of y. Half of them are on the negative side and half are on the positive side, and they balance one another out. Now let's multiply the deviations of x by the deviations of y. And notice that I'm doing this for every data point, right? And here, I know I'm going to need to find sum, so I'll sum them here. Oops. So that's my sum. I'll actually color these a different font color so that we don't get confused. And let's also find our deviations of x squared. And let's find the sum of those. So here's our two sums, and what we need to find in order to find b sub 1, so finding b sub 1, we need to find the ratio between this and that. And so our b sub 1 equals 0.125. Now that we know b sub 1, we can easily find b sub 0. Now I'll actually color these a different color. And remember, the formula for b sub 0 is just y minus b sub 1 times x, right? So, and I already have an x and y, my point of averages. So y, oops, forgot to put an equal sign. So y minus b sub 1 times x. And I get 4.75. So in order to find my equation for the line, all I do is I take those two values and put them into my actual line equation. So in order to find my predicted y, I would take 4.75 and add that to 0.125 times x. So this is my regression line for this set of data. Now, the previous example, this was actually choice C. So it actually happened to be the regression line as well. Here's the kicker, though. We need to interpret this, right? It's not good enough for us to just have this. We need to know sort of what this means. You could think of, so in order to get y, we're changing everything from fat into cost, right? Dollars, right? You could almost think of the y-intercept as sort of like a base cost, right? So 4.75 seems to be sort of the base cost for these pizzas. And then for every gram of fat, you add 12.5 cents, right? So if you have just 1 gram of fat, presumably, then you would just add 12.5 cents to this pizza. And perhaps that pizza wouldn't taste very good, but would be probably a lot healthier for you. But if you add 100 grams of fat, right? So 100 grams of fat, and each of those grams of fat is worth 0.125, right? 12.5 cents. Then you have to multiply that in order to add that to your base cost, right? So in some ways, this base cost and this is sort of acting like, it's sort of acting like, it's sort of giving you an idea of how much every gram of fat costs you, right? Because notice that as grams of fat goes up, cost goes up. And so, this data is actually slightly wrong. It's 17, or else this would be very cheap pizza. And this is 20. But so this equation is actually helping us get an idea of how much each gram of fat is costing us and exactly what the relationship is between grams of fat and cost, right? And that's the goal of the regression line.